The infinite circle. Imagine closing your eyes and drifting into a dream, not a dream of places or people, but of perfect shapes, eternal, quiet, balanced. In that silent dreamscape, a circle begins to emerge, soft and glowing, hovering in the void, completely still. A shape so simple, yet so profound. No edges, no angles, no beginning or end, just roundness. You reach out with a thread, a cosmic ruler, and measure its edge. You find its circumference. Then you stretch another thread straight through its center, the diameter. Divide the first number by the second. Circumference divided by diameter. What do you get? A number, not just any number, a number that whispers infinity. You get pi, 3.14159, and it goes on, forever. The digits of pi never end. They never repeat. No rhythm, no pattern, just an endless cascade of randomness, packed inside a single, elegant ratio. Pi is irrational. You can't write it as a simple fraction. It doesn't fit neatly on a number line, and yet it governs every circle in the universe. Thousands of years ago, civilizations chased pi. The Babylonians said pi was 3.125. The Egyptians, around 3.1605. The Greeks got closer. Archimedes, using clever geometry, trapped pi between 3.1408 and 3.1429. But none of them could ever pin it down. No one can. Not even now. Computers today have calculated pi to over 100 trillion digits, a number so long you could read one digit per second and it would take over 3 million years to finish. And we still don't know the truth about it. One question remains unanswered. Is pi a normal number? That would mean every possible sequence of digits occurs inside it. Eventually, your phone number, your birthday, the complete works of Shakespeare, the DNA of every living thing, all of it, hiding somewhere inside pi. It's like the Library of Babel, encoded into numbers, an infinite book with every truth, every lie, every dream, somewhere. But no one has proven pi is normal. We suspect it. We want it to be. But it remains a mystery. Still, we use pi every day. We build bridges with it. We explore space with it. It shows up in waves, signals, light, gravity, even in the quantum realm. It connects geometry to analysis, physics to philosophy. And yet, you can't hold it. You can't memorize it. You can't capture it fully, even with machines. Pi is like time. You know what it is. But the more you chase it, the more it escapes. Mathematicians have tried to crack it for centuries. The Indian genius, Ramanujan, wrote down infinite series that reveal digits of pi. The Chodnovsky brothers built supercomputers in their apartment just to calculate it faster. But no matter how deep we go, we're still swimming on the surface of infinity. Some people even memorize thousands of digits of pi, reciting them like mantras, chanting a number that has no pattern and no end. They do it not because it's useful, but because it feels sacred, a ritual, a meditation, a quiet act of devotion to the unknown. So now, imagine yourself falling deeper into sleep as the digits of pi fall like rain, not in chaos, but in rhythm, a rhythm so complex, so deep, that only the universe can hear it. And in that silence, the circle continues to turn, a symbol of perfection, a shape that holds infinity in its arms, a single loop containing everything, the unreachable end. Imagine standing at the edge of a quiet path. Before you, a finish line gleams in the distance, not far, just 10 meters away. You breathe slowly. You take a step forward, but something strange happens. You can't walk the full 10 meters at once. First, you must walk half the distance, 5 meters. Then, to continue, you must walk half the remaining distance, 2.5 meters. Then half of that, 1.25 meters. Then again, 0.625 meters, and so on, forever. You realize something unsettling. No matter how many steps you take, there's always another half distance left. You'll never actually reach the finish line. You are stuck. This is Zeno's paradox of motion, one of the oldest and strangest problems in mathematics. And it asks a simple question: how can anything ever move? Over 2,000 years ago, Zeno of Elea created this thought experiment to defend his teacher Parmenides, who believed that motion was an illusion. It sounds absurd, but the logic is strangely airtight. In order to go from point A to point B, you must first go halfway. But before you reach halfway, you must go half of that. And before that, half again, an infinite number of steps. But how can you complete an infinite number of tasks in a finite amount of time? Shouldn't it take you forever to finish an infinite list? So then, why can you move at all? Why can you walk, run, fall, travel, blink? Why can you cross a room when Zeno says you'll never arrive? Mathematically, this is a paradox of infinity, because the number of steps, although infinite, gets smaller and smaller. Half, then a quarter, then an eighth, then a 16th. The distances shrink. The sum of all these steps, 5 plus 2.5 plus 1.2, 5 plus, seems infinite, but it's not. Mathematicians realized something revolutionary. Even an infinite number of decreasing values can add up to something finite. This is called a convergent series. In this case, the infinite steps converge to exactly 10 meters. That means motion is possible, but only because of the strange and beautiful nature of infinity. Still, Zeno's idea haunts us, not just as a puzzle, but as a deeper reflection. It's not just about walking to a line, it's about progress, about chasing goals, about getting closer and closer and never quite arriving. Because maybe we live inside a paradox ourselves. We imagine a perfect version of ourselves at the finish line, smarter, stronger, happier. But to get there, we must always fix something, learn more, change more. We take steps, we grow, we evolve. But are we ever finished? Or are we always approaching, never arriving? Just like Zeno's traveler. In modern physics, Zeno's paradox inspired deeper questions about quantum jumps, about Planck length, the smallest measurable distance, about whether space and time are continuous or made of indivisible atoms. In quantum mechanics, there's even something called the quantum Zeno effect, where simply observing a particle too often can stop it from evolving, like watching a pot that never boils. Maybe motion is not just about space. Maybe it's about how often we measure reality. The more we try to catch movement, the more it slips away. So now, picture yourself back on that path. The world is quiet. The goal is ahead. You take a step, then another. You get closer. But somewhere in your mind, you know, the line can never be fully reached. And that's okay, because maybe the beauty of motion isn't in the arrival, but in the endless approach, in the infinite journey. And as you drift deeper into rest, the paradox continues without you, step by step, half by half, closer, always closer. The missing square puzzle. Let your mind settle. You're standing before a simple grid. Four colored shapes lie quietly on a board. A red triangle, a green shape, a small blue triangle, and a yellow wedge. They seem harmless, playful even. Now you move them around, shift them, rotate them. You place them into a perfect right-angled triangle. Everything fits. No gaps, no overlaps. Then you rearrange the same four pieces again into a right-angled triangle. Same colors, same pieces, same total space, but this time something strange happens. A tiny gap appears, a missing square. Where did it come from? You didn't remove anything. You didn't shrink or stretch the pieces. And yet, there it is, a hole that wasn't there before. This is the missing square puzzle. It's a gentle illusion, a silent rebellion against your intuition. It teaches us that even in the clean world of geometry, our minds can be misled. The puzzle was made famous by Paul Curry in the 1950s, but its roots go back much further. It appears deceptively simple. Four geometric shapes, two arrangements, one missing square. No tricks, no hidden compartments, just math and your perception. So, how is it possible? The answer hides in a subtle curve, invisible to the eye. You see, the two triangles you create with the pieces aren't actually triangles. They're hypotenuses. The longest sides aren't straight. They bend ever so slightly. One bows inward, the other bulges outward. To the naked eye, they seem straight. But geometry never lies. When you calculate the slopes of the red and blue triangles, you'll notice a discrepancy. The red triangle rises 2 units and runs 5 units, a slope of 2/5. The blue triangle rises 3 units and runs 8 units, a slope of 3/8. They aren't the same. That means the large triangle you thought you were creating isn't really a triangle at all. In the first arrangement, the hypotenuse dips inward, just enough to compensate for the area. In the second, it bulges outward, creating a tiny, empty square. 1 pixel's worth of difference hidden in the slope. This illusion shows something profound. Even with precise shapes and clear measurements, your eyes can be fooled. It's not just an error of vision, it's an error of assumption. Your brain assumes straightness where there is none. You believe you're seeing a triangle, but you're not. This puzzle doesn't just play with shapes. It whispers about perception, trust, and how even logic can lead us astray when details are missed. It reminds us that in mathematics, the tiniest difference, a single angle, a subtle line, can shift the entire truth. In your dreams tonight, imagine walking through a world built on perfect geometry, every wall straight, every corner clean. But look closer. What if the lines bend ever so slightly? What if there are spaces between what you thought was whole? The missing square puzzle is not just a visual trick, it's a meditation on error, a soft spoken lesson that what you see isn't always what is. So, as you drift into sleep, let this idea rest with you that certainty is sometimes an illusion, that even in the cleanest forms, confusion can hide, and that wonder, true wonder, often waits in the smallest gaps. Gödel's incompleteness. Imagine a vast temple built from pure logic, a place where every statement has a solid foundation, every truth is provable, and everything follows clear rules. For centuries, the ideal was simple: to find a secure, complete, and coherent foundation for all of mathematics, a world where every true statement could be proven. This was the hope, the dream of rational perfection. But in 1931, something shifted. A young logician, Kurt Gödel, showed that this dream was fundamentally flawed. He didn't shout or cause a revolution. He simply published a quiet paper that would fracture the very core of mathematics. Gödel's incompleteness theorem didn't scream chaos. Instead, it whispered a paradox so powerful that it put the entire structure of certainty into question. What did he prove? In the simplest terms, any mathematical system powerful enough to describe arithmetic is either incomplete or inconsistent. In other words, in any such system, there will always be true statements that cannot be proven, statements that are undeniably true but are beyond the reach of logic itself. This revelation was earth-shattering, not because it introduced chaos, but because it proved that even logic has boundaries. Imagine trying to write the perfect book of rules, one that describes all of mathematics. You lay down the foundation, define the terms, and create a structure that seems flawless. But Gödel's theorem tells us that no matter how complete we think the system is, there will always be truths hiding in the shadows, truths that can't be captured by any set of rules. Gödel's proof turned the dream of absolute certainty into a paradox. We are left with a haunting question: can we ever know everything? Gödel's result challenges our deepest assumptions about knowledge and truth. It shows that mathematics, the pillar of certainty, is far more mysterious than we ever imagined. And yet, despite this broken ideal, Gödel's theorem didn't destroy mathematics. Instead, it opened new doors. It inspired generations of mathematicians and philosophers to explore the limits of logic and truth. The search for understanding continues, but now, with the knowledge that some questions may forever remain beyond our reach. The Banach-Tarski mathematics is full of paradoxes that test the limits of logic and intuition. We've encountered paradoxes that question space, time, and motion. But now, we step into a more abstract world, where even basic principles of geometry and set theory are turned upside down. This is the world of the Banach-Tarski paradox, a counterintuitive result in set theory and geometry that challenges everything we know about volume, space, and the concept of infinity. Imagine, for a moment, that you have a solid ball, a sphere, perfectly round and full. According to the Banach-Tarski paradox, this ball, in a very precise and mathematical sense, can be cut into a finite number of pieces and reassembled into two identical copies of the original ball. That's right. By performing a series of complex operations, you can take one ball, divide it into a set of non-overlapping pieces, and create two new balls, each the same size and shape as the original. At first glance, this seems impossible. How can you take something solid, divide it up, and end up with more than you started with? It seems to violate everything we understand about volume and the conservation of matter. And yet, mathematically, this result is valid. The Banach-Tarski paradox is not a flaw in reasoning or a mistake. It's a logical consequence of the rules of set theory and geometry, albeit one that seems to defy physical reality. So how is this possible? The key lies in the concept of infinite sets and the idea of non-measurable sets. In traditional geometry, we are used to objects that can be measured, their sizes and volumes determined by clear rules. However, in the Banach-Tarski paradox, the pieces that make up the ball are not typical geometric objects. They are, in fact, non-measurable sets. These sets do not have a well-defined volume in the traditional sense, and as a result, the usual rules of geometry and volume do not apply. The process described by the Banach-Tarski paradox involves an infinite number of rotations and translations, a method that works only in the abstract world of mathematics, not in the physical universe. To understand this, think about the concept of infinity. Infinity is not a number or a size. It's an idea, a concept that describes something that is boundless and uncountable. When mathematicians work with infinity, they are dealing with sets that have no end, that continue indefinitely. In the Banach-Tarski paradox, the pieces you create from the original ball are actually infinite sets that have been split and rearranged in ways that are impossible in the physical world. This paradox is so mind-bending because it shows that our intuition about space, volume, and geometry is fundamentally flawed when we venture into the realm of infinite sets. We cannot intuitively grasp how the rules that apply to finite objects, things that we can touch and measure, break down when we step into the infinite. The Banach-Tarski paradox does not violate any laws of mathematics. Rather, it highlights the strange and counterintuitive nature of infinity, which often behaves in ways that are completely alien to our everyday experience. But what does this paradox tell us about the world? Does it mean that we can, in fact, take a ball and duplicate it at will? Of course not. The Banach-Tarski paradox is purely a mathematical result that exists in the abstract world of set theory and geometry. In the physical world, where we deal with atoms, molecules, and matter, such operations are impossible. The paradox shows us that our mathematical models, powerful and useful as they are, do not necessarily reflect the constraints and realities of the physical universe. However, the Banach-Tarski Paradox offers something more profound. It illustrates the power of abstract thinking and the beauty of mathematical exploration. Mathematics is not bound by the same constraints as the physical world. It operates in a realm where our intuition and everyday experiences are often irrelevant. By delving into these abstract concepts, mathematicians are able to uncover new and unexpected truths that challenge our understanding of the world. These truths don't have to make sense in the real world. They only need to make sense within the logical structure of mathematics itself. As we explore the paradox further, we encounter a deeper question. What does it mean to measure something? In the Banach-Tarski Paradox, the concept of volume itself becomes problematic. In traditional geometry, volume is a well-defined concept, but when dealing with infinite sets and non-measurable objects, the idea of volume breaks down. The pieces that make up the two new balls in the paradox don't have a measurable volume in the traditional sense. They are abstract constructs that exist only within the framework of mathematical theory. This forces us to reconsider what we mean by measurement and volume in a world that isn't confined to the physical. So, while the Banach-Tarski paradox is an intellectually fascinating result, it doesn't have any practical implications for the physical world. You won't be able to cut a ball into pieces and reassemble it into two identical copies in your living room. But the paradox does have profound implications for our understanding of mathematics, infinity, and the limits of human intuition. It reminds us that the world of mathematics is not constrained by the same rules that govern our physical reality. In the realm of infinity, anything is possible, even the impossible.